Welcome back to part 2 of my 3-part video series where we are learning how to use kinematic equations of projectile motion simply by playing Fortnite. So let's get right back into it. So in the last video, we made a little bit of an idealized situation where we shot a grenade launcher straight up into the air. There's zero reason to do that anytime when you're playing Fortnite. So this time we're going to try somewhat of a more realistic example. Because when you're playing, you're shooting at more of an angle in front of you. Not directly in front, not straight up, but an angle. You got these spawn aliens, and you can see you're shooting it at some type of arc. So now, let's use an appropriate example. Our example is going to be shooting it at an arc up and away from us at around, let's say, a 45-degree angle. And so let's slow it down into slow motion so we can see everything better. Just so we can see the path it takes. So it launches from the ground, essentially, and then it goes, and we'll stop it about right here, and so we can see where the peak of this is. So we mark the peak, and then let's state what we know, just like last time. We know we're going to start with the vertical distances and velocity. So vertical velocity, so the velocity up and down at the peak, that's going to be 0. Just like we're not talking about horizontal velocity, we're talking about up and down is 0. Just like when we shot straight up in the air. What else? Distance, the vertical distance from the ground to the peak. That we also know, or we don't know, we're trying to figure out. So that's a question mark. Also time from when it's shot to the peak, not sure, we're going to figure that out. Now, what else do we know? We shot it out at an angle this time. And that angle is roughly 45 degrees. We're going to assume it's 45 degrees for the simplicity of this video, and then we'll talk about what we do next video. Okay, so it's at 45 degrees. I'm going to mark it as such. And what else do we know? We know that the velocity of the grenade as it's shot out of the launcher from our first video, we calculated that out to be 15.7 meters per second, right? What else do we know? We also know that distance on the ground is 0, and time at the start is also 0. Now here's where it gets a little tricky. We talked about the velocity is 15.7 meters per second, but that's at the angle of which it's shot at. So that angled line that we drew. Now we need to break this up into vertical velocity, y velocity, and horizontal velocity, the velocity in the x direction. Okay, so now we can calculate the vertical velocity, vy0. And if you remember some basic trigonometry, we know that the sine of an angle is going to be the furthest side divided by the hypotenuse of that triangle. In this case, we do a sine of a 45-degree angle equals the vertical velocity vy0 divided by the velocity of the hypotenuse, which is v0. We can then rearrange that equation by moving v0 over to the other side, so we'll end up with v0 times sine of a 45-degree angle equals vy0. We know v0, we know sine 45, we can solve for the vertical velocity. And that'll turn out to be 11.1 meters per second. Plug it into any calculator. Just make sure you use degrees instead of radians. Don't forget. And next, we can solve for the horizontal velocity, vx0. And that's simply the cosine of a 45-degree angle, in the same manner that vertical was sine. So vx0 equals, and the property of a 45-degree angle is that cosine and sine are the same. So it's also 11.1 meters per second. Now, I apologize for my handwriting. I am an engineer, and we are notorious for horrible handwriting. So just stick with me here, and we will make it through. Okay, now we have enough information to solve for the first thing, which is time at the peak. So we're going to use a new kinematic equation that we haven't looked at yet, which is the velocity at the end equals initial velocity plus acceleration times time. And we can replace these basic values with our nomenclature, which is vyp, so the vertical velocity at the peak equals the vertical velocity at the base plus acceleration times the time it took to get to the peak, tp. We do a little bit of rearranging, subtract vy0 from both sides, and we'll get vyp minus vy0 equals acceleration times time. Do some more rearranging from there, and you just get time at the peak equals velocity vertical velocity at the peak minus vertical velocity at the start divided by acceleration. And we know all of these things now. So we just need to plug in our numbers and solve for the time. So time at the peak is now 0 minus 11.1 meters per second divided by negative 9.81 meters per second squared. And that will give us 1.13 seconds. So from the time it was shot to the time of the peak is 1.13 seconds. Now, keep in mind and just remember through all of this that we used the vertical distances and vertical velocities to calculate this. We're not considering horizontal velocity at all right now. We'll do that next. Before we do that, however, we still need to calculate the distance of the peak, the vertical distance of the peak. And that will use a new kinematic equation, which is v1 squared, so equals v0 squared plus 2 times acceleration times distance. And so we can substitute our values just like we have done for all the other equations. And that'll give us velocity vyp, which is vertical velocity at the peak squared, equals our starting velocity, which is vy0 squared, plus 2a acceleration times the distance of the peak, dyp, which is what we're trying to solve. And again, handwriting's poor, stick with me. I appreciate it. Okay, now we do some rearranging, and we get dyp, so the distance, vertical distance at the peak, equals the vertical velocity at the peak squared, minus the vertical velocity at the start squared, divided by 2 times acceleration. Okay, and we know all these values. We can just plug them in. We know the vertical velocity at the peak is 0. We know acceleration is gravity acting downwards, so it will be negative. Plug those numbers in, and we get vertical distance of the peak equals 0 squared, that makes it easy, minus 11.1 meters per second squared, divided by 2 times gravity, which is negative 9.81 meters per second squared. And like any good engineer knows what to do, we just plug that into a calculator, and we end up with the vertical distance at the peak equals 6.28 meters squared, or 6.28 meters, apologies. And you'll notice that that is exactly half the distance of the peak of our vertical shot. Interesting, right? Now, you might be wondering, why do we care about the vertical distance at the peak and the time it took to get there? Well, it's all necessary to calculate how far we're going to shoot this grenade, how far it'll take, and what angle we should shoot it at to hit those zombies. And that's what we're going to do in part 3 of this series. We're going to continue this flight path, just like we're going to show now, and we're going to calculate the distance that it takes, the horizontal distance now, from when we shot it to where it lands. Thank you all so much for watching. Please click part 3 of the video series, and I'll see you next time. Goodbye!